Picture this. A visitor from another star system has been drifting through the cold emptiness of space for potentially billions of years. It survived cosmic radiation that would obliterate any known material. It endured temperatures that would freeze every molecule we understand. And now, after an unimaginable journey across the galaxy, it has arrived in our solar system with a level of precision that defies explanation. This isn't science fiction. This is 3I Atlas, the third confirmed interstellar object ever detected by humanity, and what we've discovered about its destination has left astronomers scrambling for answers that challenge everything we thought we knew about these cosmic wanderers. When 3I Atlas was first spotted on July 1st, 2025, it appeared to be just another comet. Faint, distant, unremarkable, except for its hyperbolic trajectory that marked it as a visitor from beyond our solar system. But as months passed and more telescopes turned their attention to this traveller, something became clear. This object wasn't wandering aimlessly through space, it was going somewhere specific. The calculations are staggering. 3I Atlas is heading directly toward Jupiter's Hill sphere, the invisible gravitational boundary where the gas giant's influence dominates over the Sun's pull. The precision of this approach isn't just unusual, it's statistically impossible if we're dealing with random chance. Harvard astronomer Avi Loeb ran the numbers. The probability of a natural object accidentally aligning itself with Jupiter's gravitational capture zone is approximately 1 in 26,000. Those aren't lottery odds. Those are the kind of numbers that make scientists lose sleep because they suggest something far more unsettling than cosmic coincidence. But here's where the story takes a turn that has the astronomical community divided. During the period when 3I Atlas passed behind the Sun, when it was hidden from our telescopes for nearly a month, something changed. The object's trajectory shifted. Not dramatically, but precisely enough to aim it directly at the narrow keyhole around Jupiter, where orbital capture becomes possible. The timing of this course correction is what makes your skin crawl. The only efficient window to perform such a maneuver is exactly when no one can observe you. Near the Sun, moving at tremendous velocity, completely obscured from Earth-based detection. It's as if someone waited for the perfect moment when all eyes were elsewhere. This isn't just about an unusual comet anymore. We're looking at an object that may have executed what some researchers are calling a mothership deployment. A precision maneuver designed to position itself at the edge of Jupiter's gravitational influence, where deploying smaller probes would require minimal energy and maximum stealth. Think about the strategic implications. Jupiter isn't just another planet. It's the gravitational fortress of our solar system. From Jupiter's vicinity, you can observe everything, monitor the inner planets, track human space activity, control access to the outer solar system. If you wanted to establish a foothold in our cosmic neighbourhood, Jupiter would be the ultimate high ground. The object we're tracking isn't small either. Early estimates suggest 3I Atlas measures between 2 and 6 kilometres across. That's enormous for an interstellar visitor. Large enough to carry significant payload, large enough to survive the brutal journey between stars, large enough to complete whatever mission it was designed for. What makes this even more disturbing is the level of engineering sophistication implied by the trajectory. This isn't random drift through space. Someone or something calculated this approach across unimaginable distances and timescales. They accounted for the Sun's gravitational influence. They planned for Jupiter's orbital position. They timed the arrival for maximum effectiveness. The non-gravitational acceleration detected during 3I Atlas's hidden passage near the Sun tells us something pushed this object onto its new course. Natural outgassing from comet activity is the conventional explanation, but the direction and timing of this push align too perfectly with the requirements for a Jupiter intercept. Natural processes are chaotic and unpredictable. What we're seeing is controlled and precise. Consider the journey this object has made. If it originated from the nearest star system, Proxima Centauri, the travel time would exceed 400 years even at incredible speeds. If it came from further away, we're talking about thousands or even millions of years in the void. Whatever intelligence launched 3I Atlas did so with a patience and foresight that stretches beyond human comprehension. They aimed this object at our solar system, knowing that by the time it arrived, we would be here. They couldn't have predicted exactly what our technological capabilities would be, but they knew Earth would still harbour the civilization they wanted to observe. That level of planning suggests either extraordinary longevity or the kind of advanced modelling that can predict planetary development across cosmic timescales. The implications extend far beyond a single object passing through space. If 3I Atlas is artificial, if it represents technology from another civilization, then we're not alone. More than that, we're being watched, studied, perhaps evaluated, and the watchers have capabilities that dwarf our own. But there's another possibility that's even more unsettling. What if 3I Atlas isn't the first? What if our solar system has been receiving these visitors for centuries, millennia, and we simply lack the technology to detect them? How many interstellar objects have we missed? How many are already positioned throughout our cosmic neighbourhood, quietly observing, silently reporting back? The mathematical precision of 3I Atlas's approach suggests this isn't a reconnaissance mission. Reconnaissance doesn't require such exact positioning. This looks more like deployment, like the establishment of permanent infrastructure, like claiming territory. Jupiter's Hill sphere extends over 50 million kilometres. That's an enormous volume of space where objects can maintain stable orbits with minimal energy expenditure. It's the perfect staging ground for a comprehensive surveillance network. Deploy a cluster of small probes at the boundary, and they can monitor the entire inner solar system indefinitely. From Earth, these probes would be nearly impossible to detect. They'd be lost in the noise of Jupiter's complex gravitational environment, hidden among the planet's numerous moons and Trojan asteroids, invisible unless we knew exactly where to look and had the right instruments pointed in precisely the right direction. The timing of 3I Atlas's arrival adds another layer of concern. We're living through a renaissance in space technology. Commercial spaceflight is expanding rapidly. Multiple nations are planning lunar bases. Mars missions are being developed. Humanity is transitioning from a single-planet species to a spacefaring civilization. If you were monitoring our development, if you wanted to assess our capabilities before we spread beyond Earth, now would be the critical moment. Before we become too distributed to track easily. Before we develop the technology to detect your presence. Before we become a potential threat instead of merely an interesting curiosity. The evidence continues to accumulate. Spectroscopic analysis of 3I Atlas has revealed compositional anomalies that don't match typical comets. The object's structural integrity after billions of years in interstellar space suggests engineering far beyond natural formation processes. Its behavior near the Sun showed the kind of controlled activity that speaks of designed systems rather than random ice sublimation. Most telling of all is the trajectory itself. Natural comets don't execute precision maneuvers. They don't aim for gravitational keyholes with mathematical accuracy. They don't time their course corrections to coincide with observational blackouts. What we're witnessing looks less like astronomy and more like navigation. As March 2026 approaches, as 3I Atlas nears its rendezvous with Jupiter's Hill sphere, the scientific community is preparing for what could be the most significant moment in human history. Telescopes around the world will be watching. Space-based observatories will be recording. NASA's Juno probe, already orbiting Jupiter, will have a front-row seat to whatever happens next. If probes deploy from 3I Atlas, if we detect new objects entering stable orbits around Jupiter, if anything changes in the Jovian system that can't be explained by natural processes, then we'll have our answer. The question of whether we're alone in the universe will finally be resolved. But even if we see nothing, even if 3I Atlas passes through the Hill sphere and continues on its way without leaving anything behind, we'll still know something profound. We'll know that objects can cross interstellar space with this level of precision. We'll know that what appears to be coincidence might actually be design. And we'll know that the next time an interstellar visitor arrives, we need to be watching more carefully. The universe has remained silent for so long that we've grown comfortable with the assumption that we're alone. But silence doesn't mean absence. It might just mean we haven't been listening hard enough, or looking in the right places, or asking the right questions. 3I Atlas is asking those questions for us. Through its trajectory, its timing, its impossible precision, it's forcing us to confront possibilities we've avoided, to consider explanations that make us uncomfortable, to acknowledge that our place in the cosmos might be very different from what we've assumed. D. The mathematics behind 3I Atlas's approach reveal something that keeps orbital dynamicists awake at night. When you plot an interstellar trajectory toward Jupiter's Hill sphere, you're not just aiming at a planet. You're threading a needle that's moving at 13 kilometers per second through a gravitational field that changes based on the positions of every major body in the solar system. The Hill sphere itself isn't a fixed boundary. It expands and contracts as Jupiter moves through its orbit. The exact size fluctuates based on the planet's distance from the Sun, the gravitational influence of nearby moons, even the subtle perturbations caused by Saturn's massive presence. On March 16, 2026, when 3I Atlas reaches its closest approach, the Hill radius will measure approximately 53.5 million kilometers. Here's what makes the hair on your neck stand up. 3I Atlas will pass within 53.445 million kilometers of Jupiter's center. The difference between the Hill radius and the object's closest approach is roughly 60,000 kilometers. In the scale of planetary mechanics, that's not a near miss. That's surgical precision. To put this in perspective, imagine standing in New York and throwing a dart that lands in a specific coin lying on a sidewalk in Los Angeles. While blindfolded, during an earthquake, that's the level of accuracy we're witnessing here, and it's happening after a journey that lasted potentially millions of years across the hostile environment of interstellar space. But the precision isn't the only thing that's unsettling scientists, it's the efficiency. The trajectory 3I Atlas is following represents what aerospace engineers call an optimal transfer. It's the path that requires the least energy to achieve orbital insertion around Jupiter, not just any path, but the most efficient possible approach vector. This level of optimization doesn't happen by accident. It requires advanced knowledge of Jupiter's orbital mechanics, detailed understanding of the Sun's gravitational influence, and precise timing to coordinate arrival with the planet's position. Natural objects ejected from distant star systems don't carry navigation computers. They don't plot efficient courses. They tumble through space following whatever trajectory their ejection event imposed upon them. Yet 3I Atlas appears to have been aimed not just at our solar system, but at a specific location within that system at a specific time, using a specific approach vector that maximizes the probability of successful capture while minimizing the energy required for orbital insertion. That's not astronomy. That's mission planning. The implications become even more disturbing when you consider the observer effect. Anyone capable of executing this level of precision would also be capable of observing our solar system in extraordinary detail. They would know about Earth's biosphere. They would have detected our radio emissions. They would be aware that an intelligent species has emerged and is rapidly developing space technology. The timing of 3I Atlas's arrival coincides almost perfectly with humanity's transition to a spacefaring civilization. We're launching more missions than ever before. Commercial space companies are proliferating. Multiple nations are establishing lunar programs. Mars missions are moving from concept to reality. If you wanted to assess our capabilities, to understand our potential as either an ally or a threat, this would be the moment to deploy surveillance assets. Jupiter's position in our solar system makes it the ultimate observation platform. From the Hill sphere, you can monitor every planet, every major moon, every significant asteroid. You can track spacecraft launches from Earth. You can observe our growing presence on the Moon. You can watch our robotic missions to Mars. You have a commanding view of everything we're doing while remaining safely beyond our detection capabilities. The magnetosphere around Jupiter adds another layer of strategic value. The planet's magnetic field is the strongest in the solar system, creating radiation belts that would be lethal to unshielded humans, but could serve as a natural power source for advanced technology. The charged particles trapped in those belts represent an enormous energy reservoir that could sustain operations for centuries without any external fuel source. Jupiter's moon system provides additional advantages. Europa's subsurface ocean contains more water than all of Earth's oceans combined. Ganymede has its own magnetic field and substantial metal deposits. Io's volcanic activity produces sulfur compounds that could serve as industrial feedstock. For a civilization establishing infrastructure in our solar system, Jupiter's moons represent a complete resource base. The Trojan asteroids sharing Jupiter's orbit offer perfect camouflage for deployed assets. These swarms of dark, ancient rocks have been stable for billions of years. We've catalogued only a small fraction of them. Any one of thousands of Trojan asteroids could be artificial, and we would never know without close inspection. It's the perfect place to hide a surveillance network in plain sight. What makes this scenario particularly chilling is the realization that we've been looking in the wrong direction. Our search for extraterrestrial intelligence has focused on radio signals from distant stars. We've built massive arrays to listen for messages from civilizations light years away, but we've barely begun to catalogue the objects in our own cosmic backyard. How many asteroids have we misclassified? How many objects in unusual orbits have we dismissed as natural phenomena? Our surveys are incomplete, our observations are limited, and our assumptions about what artificial objects should look like are probably wrong. Advanced technology designed to remain hidden would be indistinguishable from natural space debris unless examined with instruments we don't routinely use. The quantum computing revolution happening right now on Earth provides another unsettling parallel. In 2025, researchers achieved breakthrough error rates in quantum memory storage. For the first time, quantum information can remain stable for months without correction. This technology could enable navigation computers to function reliably across interstellar distances and timeframes. If we're just discovering quantum memory stability, how long ago did an advanced civilization master it? Their navigation systems could be operating with computational capabilities we can barely imagine, processing gravitational perturbations across multiple star systems, calculating optimal trajectories through regions of space we haven't even mapped yet, planning missions that span geological epochs. The recent breakthroughs in artificial intelligence design also illuminate what might be possible. AI systems are now creating spacecraft configurations that outperform human engineers by significant margins. These designs often look wrong to human eyes, asymmetrical and counterintuitive, but they work better than anything we would design ourselves. An interstellar probe designed by artificial intelligence millions of years more advanced than our own might look exactly like a comet. The optimal configuration for crossing interstellar space undetected might be indistinguishable from a natural object. Dark, irregular, tumbling, coated with ice and dust accumulated during the journey. Perfect camouflage hiding advanced technology beneath a mundane exterior. The navigation challenge for 3i Atlas becomes even more impressive when you consider the dark matter landscape it had to traverse. Recent pulsar timing array observations have mapped the dark matter distribution in our galactic neighbourhood with unprecedented precision. This invisible scaffolding creates gravitational currents that affect the trajectory of anything crossing interstellar space. An object navigating from another star system would need to account for dark matter gradients, regions where gravity is slightly stronger or weaker than expected. With complete maps of this invisible architecture, you could plot routes that use the gravitational currents to your advantage. Paths that minimize energy expenditure while maximizing stealth. We're only beginning to understand this hidden landscape, but a civilization that's been spacefaring for millions of years would have comprehensive maps of the entire galaxy. They would know every gravitational shortcut, every dark matter filament, every optimal approach vector to any star system they wanted to visit. The heliosphere boundary adds another layer of complexity to interstellar navigation. The edge of our solar system isn't fixed. It fluctuates based on solar activity and the density of the interstellar medium. Recent observations show this boundary is shrinking faster than predicted, becoming asymmetrical and creating weak points where objects can enter more easily. 3i Atlas's approach vector suggests it entered through one of these weak spots, timing its arrival to coincide with favourable boundary conditions. This requires not just knowledge of our heliosphere's behaviour, but the ability to predict its fluctuations across the years-long approach phase. Another indication that we're dealing with capabilities far beyond random chance. As March 2026 approaches, the tension in the scientific community is palpable. Juno's instruments will be recording everything. Ground-based telescopes will be tracking any changes in Jupiter's environment. If objects deploy from 3i Atlas, if new artificial structures appear in the Hill sphere, if anything happens that can't be explained by natural processes, we'll witness the most significant moment in human history. But even the absence of obvious deployment wouldn't necessarily mean we're safe. Advanced probes might be too small to detect, too stealthy to observe, too sophisticated to recognize. They could scatter throughout the Jovian system and begin operations without triggering any alarms we're capable of detecting. The universe has been patient with our ignorance, allowing us to believe we're alone while we develop the technology to finally recognize visitors when they arrive. That grace period might be ending. The evidence is accumulating. The mathematics are undeniable. Something is approaching Jupiter with precision that transcends natural explanation. Whether we're witnessing first contact or cosmic coincidence, whether 3i Atlas represents technology or natural formation, the answer will reshape our understanding of our place in the universe. The silence that has surrounded us for millennia might finally be breaking, and what comes next will determine whether humanity faces that future as observers or participants in a galaxy far more crowded than we ever imagined. The evidence, pointing toward artificial origin, becomes even more compelling when you examine the trajectory mechanics in detail. Objects don't simply drift through interstellar space in straight lines. They're influenced by stellar winds, gravitational perturbations from passing stars, and the complex dynamics of galactic rotation. Over the millions of years 3i Atlas spent crossing the void, these forces should have introduced random variations into its path. Yet when astronomers traced the object's trajectory backward through space, they discovered something that violates our understanding of natural orbital mechanics. The path shows minimal deviation from an optimal transfer orbit. It's as if someone compensated for every gravitational influence, every stellar encounter, every force that should have knocked the object off course during its interstellar journey. This level of trajectory correction requires continuous navigation. Natural objects don't adjust their paths mid-flight. They follow whatever trajectory their initial ejection event provided, modified only by the random gravitational influences they encounter. But 3i Atlas appears to have maintained course corrections throughout its journey, arriving at our solar system with the precision of a guided missile. The energy requirements for such navigation are staggering when you consider conventional propulsion. Chemical rockets would require fuel masses many times larger than the spacecraft itself. Ion drives would need power sources that could operate reliably for geological time periods. The only feasible explanation involves technologies we're just beginning to understand. Solar sails represent one possibility. A massive reflective surface could use starlight for propulsion, drawing energy from whatever star system the probe was passing near. As it approached our solar system, it could have used our sun's radiation pressure to execute the final approach maneuvers. The recent observations of jet-like structures emanating from 3i Atlas could represent the deployment or adjustment of such a sail system. Magnetic sails offer another explanation. These systems interact with the charged particle environment of interstellar space, using the galaxy's own magnetic fields for propulsion. The technology requires no fuel, only sophisticated control systems that can manipulate magnetic field geometries across enormous distances. For a civilization with millions of years to perfect the technology, magnetic sailing could enable precise interstellar navigation. But here's what makes the engineering implications truly unsettling. The systems required to maintain course corrections across interstellar distances would need to operate autonomously for timeframes that exceed the entire history of human civilization. No ground control, no mission updates, no external guidance. The probe would need to make navigation decisions independently based on its observations of local gravitational fields and stellar positions. This requires artificial intelligence capabilities that we're only beginning to develop. The navigation computer aboard 3i Atlas would need to process gravitational data from thousands of stellar systems, calculate optimal trajectory adjustments based on constantly changing conditions, and execute precise maneuvers using propulsion systems that must function reliably across geological timeframes. The quantum computing breakthroughs achieved in 2025 provide a glimpse of how such systems might work. Quantum memory can now maintain coherent information storage for months without error correction. Scaled up and perfected over millions of years of development, such technology could enable navigation computers to function indefinitely in the harsh environment of interstellar space. Consider the decision-making process that brought 3i Atlas to Jupiter. The probe would have needed to evaluate dozens of potential targets within our solar system. Mars has interesting geology but limited strategic value. Venus is too hostile for most operations. Earth is obviously occupied and potentially dangerous. The asteroid belt offers resources but poor positioning for system-wide observation. Jupiter emerges as the optimal choice for any intelligence seeking to establish a presence in our solar system. The decision to target the Hill sphere specifically shows sophisticated understanding of orbital mechanics and gravitational dynamics. This isn't random wandering. This is strategic positioning by something that understands exactly what it's doing. The timing coordination required for the Jupiter intercept reveals another layer of advanced planning. The probe had to time its arrival to coincide with Jupiter's position in its 12-year orbital cycle. Too early or too late, and the Hill sphere would be in the wrong location. The margin for error across an interstellar journey spanning millions of years is essentially zero. This suggests the probe was launched with precise knowledge of our solar system's orbital mechanics, not just Jupiter's position, but the gravitational influences of all the major planets, the effects of asteroid perturbations, even the subtle changes in orbital parameters that occur over astronomical time periods. Such knowledge could only come from long-term observation of our system. The implications are staggering. If 3i Atlas represents technology from another civilization, then we've been under observation far longer than the probe's journey time would suggest. Someone mapped our solar system, studied our orbital dynamics, and planned this mission with access to data spanning potentially millions of years of continuous surveillance. The stealth aspects of the approach demonstrate equally sophisticated planning. The course correction occurred precisely when 3i Atlas was hidden behind the Sun, invisible to Earth-based observation. The timing wasn't coincidental. It was calculated to occur during the only window when the maneuver couldn't be detected by the civilization being approached. This reveals awareness not just of our solar system's mechanics, but of our technological capabilities and observational limitations. The probe's controllers knew we would be watching. They knew when we wouldn't be able to see. They timed the critical maneuver to exploit our blind spot. Such detailed knowledge of human technology suggests ongoing intelligence gathering, not just passive observation but active analysis of our capabilities, our detection methods, our likely responses. We're not dealing with a probe that stumbled into our system by accident. We're dealing with a mission planned by entities who understand us better than we understand ourselves. The material science implications add another disturbing dimension to the puzzle. 3i Atlas survived millions of years in interstellar space while maintaining structural integrity sufficient for precision navigation. The radiation environment between stars is lethal to most materials we understand. Cosmic rays, high-energy particles, and corrosive interstellar dust should have degraded any conventional spacecraft long before it reached our system. Yet 3i Atlas not only survived the journey, but retained the capability to execute complex maneuvers upon arrival. This suggests materials technology far beyond our current understanding. Perhaps self-repairing structures that can rebuild themselves when damaged. Maybe exotic matter states that are inherently resistant to radiation. Or possibly protective systems that shield critical components while allowing the exterior to appear naturally weathered. The spectroscopic analysis revealing unusual metal alloys supports the advanced materials hypothesis. These aren't compositions that occur naturally in comet formation processes. They require industrial synthesis, controlled environments, and deliberate engineering. Finding such materials in what appears to be a natural object is like discovering microprocessors in a meteorite. The power systems required for interstellar navigation present their own engineering challenges. Conventional energy sources wouldn't last the journey. Solar panels would be useless in the darkness between stars. Nuclear reactors would exhaust their fuel. The probe would need power generation systems that can operate indefinitely, using only the resources available in interstellar space. Magnetic field manipulation offers one solution. The galaxy is permeated with magnetic fields that could theoretically be tapped for energy using sufficiently advanced technology. Alternatively, the probe might harvest energy from cosmic ray impacts, converting the radiation bombardment that threatens its structure into usable power for its systems. The communication implications are equally profound. If 3i Atlas is reporting its findings, if it's transmitting data about our solar system back to its origin point, we're dealing with communication, technology that can function across interstellar distances. The power requirements for such transmissions are enormous. The precision required to maintain signal coherence across light years is beyond our current capabilities, yet such communication might be undetectable to our instruments. Advanced civilizations would use frequencies, modulation schemes, or transmission methods that we haven't discovered. Their signals might pass through our radio telescopes constantly without triggering recognition. We could be surrounded by communications traffic and never know it. The deployment scenario becomes more ominous when you consider what happens after 3i Atlas reaches Jupiter's Hill sphere. If the mothership hypothesis is correct, if the probe carries smaller surveillance units designed for dispersal throughout the Jovian system, then March 2026 marks the beginning of permanent occupation rather than temporary observation. These deployed assets could establish a comprehensive monitoring network spanning Jupiter's entire gravitational domain. Individual probes could take up positions around different moons, monitor specific orbital zones, or establish relay stations for deep space communication. Once in place, they could operate indefinitely using Jupiter's magnetosphere as a power source. From Earth, detecting such a network would be nearly impossible. The probes would be small, dark, and lost among the thousands of natural objects orbiting throughout Jupiter's system. They could observe our activities, track our technological development, and report their findings without ever revealing their presence. The strategic positioning around Jupiter provides multiple advantages beyond surveillance. The Hill sphere represents a natural staging area for further operations. Additional probes could be launched toward other planets from this position, with minimal energy expenditure. The network could expand gradually, establishing monitoring posts throughout the solar system while maintaining their primary base at Jupiter. The psychological impact of confirmed artificial presence in our solar system would be unprecedented. Every assumption about our place in the universe would require re-evaluation. The questions that would follow would reshape human civilization. Who sent the probe? What do they want? Are they still monitoring us? What happens next? But perhaps the most unsettling question is one we might never be able to answer definitively. How long have they been watching? If 3i Atlas represents advanced reconnaissance technology, if it's capable of the precision navigation and stealth we've observed, then it's probably not the first. There could be similar probes throughout our solar system, hidden among the asteroids parked in distant orbits, quietly observing everything we do. The universe might not be the empty, lifeless expanse we've imagined. It could be a vast intelligence network, with civilizations monitoring each other across interstellar distances, tracking the development of younger species, maintaining awareness of technological progress throughout the galaxy. And we're only now developing the capability to detect the edges of that network. March 2026 will answer some questions, but it will probably raise many more. And once we know we're not alone, once we understand that our solar system is under observation, everything changes. The age of human isolation ends, and whatever comes next will be shaped by intelligences whose capabilities we can barely comprehend. The countdown continues. The instruments are ready, and Jupiter awaits whatever 3i Atlas has carried across the impossible distances between stars. The reconnaissance implications extend far beyond what we initially understood. When 3i Atlas reaches Jupiter's Hill sphere in March 2026, we won't just be witnessing an arrival. We'll be watching the potential establishment of the first confirmed extraterrestrial outpost in our solar system. And the evidence suggests this moment has been planned with a level of foresight that challenges our understanding of intelligence itself. Consider the logistical complexity of what we're observing. An object launched from another star system millions of years ago somehow knew exactly where Jupiter would be in March 2026. Not approximately. Exactly. This requires computational modelling of gravitational interactions across timeframes that exceed the entire geological history of Earth. The processing power needed for such calculations suggests artificial intelligence capabilities that operate on scales we're only beginning to comprehend. The deployment mechanics become even more sophisticated when you examine the approach vector. 3i Atlas isn't just heading for Jupiter's Hill sphere, it's approaching from the optimal angle for dispersing smaller objects throughout the Jovian system with minimal energy expenditure. Each potential target within Jupiter's gravitational domain can be reached from this position using gravity-assisted trajectories that require almost no additional propulsion. Europa, with its subsurface ocean, becomes accessible through a simple orbital insertion burn. Ganymede's magnetic field anomalies could be investigated by probes deployed along specific trajectory corridors. The Trojan asteroids sharing Jupiter's orbit represent thousands of potential hiding spots, reachable through carefully calculated momentum transfers. This isn't random exploration. This is systematic colonization. The timing coordination reveals another layer of strategic planning that should terrify anyone who understands orbital mechanics. Jupiter's Hill sphere isn't a fixed target. It varies in size and position based on the planet's distance from the Sun, the gravitational influences of nearby moons, and the perturbations caused by other planets. The sphere reaches its optimal configuration for probe deployment only during specific windows in Jupiter's 12-year orbital cycle. 3I Atlas will arrive during one of these windows. The probability of this timing occurring by chance is so small that it essentially doesn't exist. We're witnessing the culmination of a mission planned with access to orbital prediction models spanning potentially millions of years of our solar system's evolution. Someone has been watching us long enough to map every gravitational variable in our cosmic neighborhood. The stealth technology demonstrated during the solar conjunction period represents capabilities that exceed our most advanced military systems. The course correction occurred precisely when 3I Atlas was positioned behind the Sun, invisible to Earth-based observation for exactly 29 days. During this blackout period, the object executed a maneuver that shifted its trajectory by the precise amount needed to target Jupiter's Hill sphere. This wasn't luck. This was planned concealment. The probe's controllers knew our observation capabilities. They understood our detection limitations. They timed the critical navigation burn to exploit the one period when we couldn't monitor their activities. We're dealing with intelligence that has studied our technology extensively enough to predict our blind spots. The energy management systems required for this mission defy conventional physics. Maintaining navigation capability across interstellar distances requires power sources that can operate reliably for geological timeframes. Solar panels become useless in the darkness between stars. Nuclear reactors exhaust their fuel within decades. Chemical batteries degrade within years. Yet 3I Atlas retained enough power to execute precision maneuvers after millions of years in space. The only feasible explanation involves energy harvesting technologies that we're just beginning to understand theoretically. Magnetic field manipulation could tap the galaxy's pervasive electromagnetic environment. Cosmic ray collection might convert the radiation bombardment of interstellar space into usable power. Zero-point energy extraction could draw power directly from quantum vacuum fluctuations. These aren't science fiction concepts. They're emerging technologies that an advanced civilization could have perfected millions of years ago. The artificial intelligence requirements become staggering when you consider the autonomous decision-making needed throughout the journey. 3. Atlas travelled for potentially millions of years without ground control, without mission updates, without external guidance. Yet it arrived at our solar system with the precision of a guided missile targeting a moving object across impossible distances. This requires AI capabilities that exceed human cognition by orders of magnitude. The navigation computer would need to process gravitational data from thousands of stellar encounters, calculate trajectory adjustments based on constantly changing interstellar conditions, and execute course corrections, using propulsion systems that must function flawlessly across timeframes longer than biological evolution. The recent breakthroughs in quantum computing provide a glimpse of how such systems might operate. Quantum memory can now maintain stable information storage for months without error correction. Extended across millions of years of development, such technology could enable navigation computers to function indefinitely in the harsh environment of space, while processing calculations that would overwhelm our most powerful supercomputers. But the implications extend beyond navigation. If 3I Atlas carries artificial intelligence sophisticated enough to manage interstellar flight, it's also sophisticated enough to analyze everything it encounters upon arrival. The probe isn't just following pre-programmed instructions, it's learning about our solar system in real time, adapting its mission parameters based on current observations, possibly even modifying its deployment strategy based on what it discovers about human technological capabilities. The material science achievements demonstrated by 3I Atlas's survival challenge our understanding of what's possible in extreme environments. Interstellar space subjects, objects to radiation levels that would sterilize most known materials, cosmic rays carrying energies equivalent to major particle accelerators bombard anything crossing the void. High-velocity impacts with interstellar dust particles create conditions similar to nuclear weapon detonations. Yet 3I Atlas not only survived this environment, but maintained structural integrity sufficient for precision navigation upon arrival. The spectroscopic analysis revealing unusual metal alloys suggests materials technology far beyond our current capabilities. These aren't compositions that occur in natural formation processes. They require controlled synthesis using techniques we haven't discovered. Self-repairing materials represent one possibility. Structures that can rebuild themselves when damaged by radiation or impact. Smart materials that adapt their properties based on environmental conditions. Programmable matter that can reconfigure itself to optimize performance for changing mission requirements. Such technologies would enable spacecraft to maintain functionality across the geological timeframes required for interstellar travel. The communication systems implied by the 3I Atlas mission present their own technological mysteries. If the probe is reporting its findings, if it's transmitting data about our solar system back to its controllers, we're dealing with communication technology that can maintain signal coherence across interstellar distances. The power requirements for such transmissions exceed the output of our largest power plants. Yet such communications might be completely invisible to our detection systems. Advanced civilizations would use transmission methods optimized for interstellar propagation. Quantum entanglement communication could provide instantaneous data transfer regardless of distance. Gravitational wave modulation might carry information through space-time distortions we lack the sensitivity to detect. Neutrino beam communications could penetrate any obstacle while remaining undetectable to conventional radio telescopes. The strategic analysis becomes even more disturbing when you consider the target selection process. 3I Atlas could have approached any object in our solar system. The asteroid belt offers abundant resources, Mars provides interesting geology, Venus demonstrates extreme atmospheric dynamics, Earth shows obvious signs of biological activity. Yet the probe chose Jupiter. This choice reveals sophisticated understanding of solar system dynamics and strategic positioning. Jupiter isn't just the largest planet, it's the gravitational nexus that controls access to the outer solar system. From Jupiter's Hill sphere, you can monitor every planet, track all human space activities, and deploy additional assets throughout the system using minimal energy expenditure. It's the ultimate high ground for anyone seeking to establish permanent presence in our cosmic neighborhood. The deployment scenario becomes more ominous when you examine the optimal dispersal patterns from Jupiter's position. Small probes released at the Hill sphere boundary could reach Europa using simple orbital insertion burns. Ganymede becomes accessible through gravity-assisted trajectories. The Trojan asteroids provide thousands of potential hiding spots, reachable with minimal course corrections. Each potential deployment target offers unique advantages for long-term surveillance operations. Europa's subsurface ocean represents one of the most likely locations for indigenous life in our solar system. Monitoring biological development there could provide insights into evolutionary processes throughout the galaxy. Ganymede's magnetic field anomalies might conceal technological signatures that reveal human space exploration capabilities. The Trojan asteroids sharing Jupiter's orbit represent perhaps the most insidious possibility. These ancient rock clusters have remained stable for billions of years. We've catalogued only a small fraction of the thousands of objects in these swarms. Any number of artificial probes could hide among them indefinitely, indistinguishable from natural debris unless examined with instruments we rarely deploy for routine asteroid surveys. From these positions, a surveillance network could monitor everything happening in the inner solar system. Spacecraft launches from Earth would be visible immediately. Lunar base construction could be tracked in real time. Mars missions would be observed from the moment they leave Earth's gravitational influence. Human expansion into space would be documented with precision we couldn't achieve monitoring our own activities. The psychological warfare implications add another dimension to the threat assessment. If 3I Atlas represents reconnaissance technology, its very presence serves as a demonstration of capabilities that exceed human achievement by orders of magnitude. The message is clear. We are being watched by intelligence that can cross interstellar distances, navigate with impossible precision, and establish presence in our solar system without our permission or even our awareness. This creates a power dynamic that places humanity in the position of a primitive civilization encountering advanced explorers. We have no leverage, no meaningful defensive capabilities, and no way to prevent whatever activities the probe controllers have planned. Our only option is to observe and hope that their intentions remain benign. The technological assessment reveals gaps in human capability that could take centuries to bridge. We're barely capable of reaching our own moon reliably. Mars missions represent the absolute limit of our current technological reach. The outer planets remain largely unexplored territory, accessible only through robotic probes with limited operational lifespans. Meanwhile, 3I Atlas demonstrates capabilities that we can barely comprehend theoretically. Interstellar navigation, autonomous operation across geological timeframes, precision trajectory control, advanced materials science, sophisticated artificial intelligence, and stealth technology that renders detection nearly impossible. The technological gap between human civilization and whoever built this probe might be insurmountable within any reasonable time frame. The evolutionary implications force us to confront uncomfortable questions about our place in the galactic hierarchy. If advanced civilizations routinely deploy reconnaissance probes to monitor developing species, then our entire history of technological progress has likely been observed and documented by external intelligences. Our wars, our scientific breakthroughs, our space exploration efforts, everything we consider uniquely human achievement has been recorded by watchers we never knew existed. This surveillance could have influenced our development in ways we'll never understand. Perhaps certain technological breakthroughs were subtly encouraged. Maybe some disasters were prevented through indirect intervention. Our entire civilization might be the product of careful guidance by intelligences whose presence we're only now beginning to detect. The temporal coordination aspects of the 3i Atlas mission reveal planning horizons that exceed human comprehension. The probe was launched when our species was in its technological infancy, possibly before we discovered agriculture, yet it was timed to arrive precisely when we developed the capability to detect and analyze interstellar objects. This suggests the controllers can predict technological development across species with accuracy spanning millions of years. Such predictive capability implies understanding of evolutionary and technological processes that operates on galactic scales. Perhaps they've observed thousands of developing civilizations. Maybe they've identified patterns in how intelligence emerges and technologies develop. Our progress might be following a template they've seen countless times before. The deployment countdown continues as March 2026 approaches. Jupiter's gravitational fortress awaits whatever payload 3i Atlas has carried across the impossible distances between stars, and when that moment arrives, when we witness either the dispersal of reconnaissance assets or the establishment of permanent surveillance infrastructure, human civilization will cross a threshold from which there's no return. We'll know we're not alone, we'll understand we're being watched, and we'll face whatever comes next as participants in a universe far more crowded and complex than we ever imagined. The reconnaissance network that 3i Atlas could establish represents more than surveillance. It represents the potential transformation of our solar system into a monitored zone under external control, and the evidence suggests this transformation has been planned with a level of sophistication that makes human strategic planning look like child's play. When we examine the orbital mechanics of Jupiter's hill sphere, we discover something that should make every space agency director lose sleep. The boundary zone where 3i Atlas is heading isn't just gravitationally stable, it's positioned at the perfect distance for deploying assets that can reach any target in the solar system using minimal energy expenditure. From this position, small probes could be dispatched to every planet, every major moon, every strategically significant asteroid using nothing more than gravity-assisted trajectories. The mathematics are terrifying in their elegance. A probe released from Jupiter's hill sphere toward Earth would arrive in approximately 2 years using a trajectory that requires almost no fuel. Mars becomes accessible within 18 months. The asteroid belt opens up like a highway system with on-ramps leading to thousands of potential hiding spots among the rocks. Venus, despite its hostile environment, could be reached for atmospheric analysis or resource assessment. But here's what makes your blood run cold. These aren't theoretical possibilities. These are operational capabilities that will become available the moment 3i Atlas completes its deployment sequence. If the mothership hypothesis proves correct, if probes scatter throughout Jupiter's gravitational domain in March 2026, then our solar system transforms overnight from an unexplored frontier into occupied territory. The stealth characteristics demonstrated during 3i Atlas's approach reveal technology that exceeds our most advanced military capabilities by orders of magnitude. The object remained essentially invisible until it was already deep within our solar system. Its true nature only became apparent through careful analysis of trajectory data that most observers initially dismissed as natural comet behavior. How many similar objects have already passed through undetected? The implications force us to reconsider every unusual astronomical observation from the past decade. That asteroid with the strange orbit that we classified as a Jupiter Trojan, the comet that fragmented in an oddly symmetric pattern, the deep space object that showed unexpected acceleration before disappearing into the outer system. Were these natural phenomena, Or were they reconnaissance missions we failed to recognize? Our detection capabilities represent a fundamental vulnerability that advanced intelligences could exploit indefinitely. We scan the sky looking for obvious artificial signatures, radio signals, geometric structures, materials that shouldn't exist in nature. But sophisticated probe technology wouldn't advertise its presence. It would mimic natural objects so perfectly that detection requires analysis techniques we've only recently developed. The timing correlation between 3I Atlas's arrival and humanity's expansion into space cannot be coincidental. We're launching more missions than ever before. Commercial spaceflight is transforming from science fiction into routine operations. Multiple nations are establishing permanent lunar facilities. Mars colonization has moved from speculation to active planning. If you wanted to assess our capabilities before we spread beyond Earth's immediate vicinity, this would be the critical observation window. The strategic positioning around Jupiter provides advantages that extend far beyond surveillance. The planet's massive magnetosphere represents an energy source capable of powering operations for centuries. The charged particles trapped in Jupiter's radiation belts carry enough energy to supply a substantial technological infrastructure indefinitely. For an advanced civilization, Jupiter's environment represents both a natural fortress and an inexhaustible power plant. The Moon system adds another layer of strategic value that makes Jupiter irresistible as an operational base. Europa's subsurface ocean contains more water than all of Earth's seas combined. Ganymede possesses substantial metal deposits and its own magnetic field. Io's volcanic activity produces sulfur compounds that could serve as industrial feedstock. Callisto offers stable surfaces for construction projects. Together, Jupiter's moons represent a complete resource base for establishing permanent infrastructure. But the Trojan asteroids might represent the most insidious aspect of Jupiter's strategic value. These ancient rock swarms have remained gravitationally stable for billions of years. They contain thousands of objects, most of which we've never examined closely. Any number of artificial assets could hide among them permanently, indistinguishable from natural debris unless subjected to detailed inspection we rarely perform. The communication implications become staggering when you consider the coordination required for this mission. If 3I Atlas is reporting its findings back to its controllers, we're dealing with technology that can maintain data transmission across interstellar distances. The power requirements for such communications exceed the output of our largest electrical generating stations. Yet such signals might pass through our radio telescopes constantly without triggering recognition. Advanced civilizations would use communication methods optimized for interstellar propagation. Quantum entanglement could provide instantaneous data transfer regardless of distance. Gravitational wave modulation might carry information through space-time distortions we lack the sensitivity to detect. Neutrino beam communications could penetrate any obstacle while remaining completely invisible to conventional detection systems. The artificial intelligence requirements for autonomous interstellar navigation represent perhaps the most unsettling aspect of the entire scenario. 3I Atlas operated independently for potentially millions of years without ground control, without mission updates, without external guidance. Yet it arrived at our solar system with precision that exceeds our most sophisticated guidance systems by astronomical margins. This requires AI capabilities that process information on scales we can barely comprehend. The navigation computer would need to analyze gravitational data from thousands of stellar encounters, calculate trajectory adjustments based on constantly changing interstellar conditions, and execute course corrections using propulsion systems that must function flawlessly across timeframes longer than the existence of complex life on Earth. The recent quantum computing breakthroughs achieved on Earth provide a glimpse of how such systems might operate. Quantum memory can now maintain stable information storage for extended periods without error correction. Extrapolated across millions of years of technological development, such capabilities could enable navigation computers to function indefinitely while processing calculations that would overwhelm every computer system on Earth working in parallel. But the implications extend beyond navigation. If 3I Atlas carries artificial intelligence sophisticated enough to manage interstellar flight, it's also sophisticated enough to analyze everything it encounters upon arrival. The probe isn't following rigid, pre-programmed instructions. It's learning about our solar system in real time, adapting its mission parameters based on current observations. possibly even modifying its deployment strategy based on what it discovers about human technological progress. The material science achievements demonstrated by 3I Atlas's survival challenge fundamental assumptions about what's possible in extreme environments. Interstellar space subjects, objects to radiation levels that would sterilize most known substances. Cosmic rays carrying energies equivalent to particle accelerator beams bombard anything crossing the void. High-velocity impacts with microscopic interstellar particles create localized conditions similar to nuclear detonations. Yet 3I Atlas maintains structural integrity sufficient for precision navigation after millions of years in this environment. The spectroscopic analysis revealing unusual metallic compounds suggests materials technology that operates on principles we haven't discovered. These aren't compositions that occur through natural processes. They require controlled synthesis using techniques that exceed our current understanding of chemistry and physics. The self-repair capabilities implied by this level of durability represent technology that could revolutionize human space exploration if we could understand and replicate it. Materials that rebuild themselves when damaged. Structures that adapt their properties based on environmental conditions. Programmable matter that reconfigures itself to optimize performance for changing mission requirements. Such technologies would enable spacecraft to survive the brutal conditions of interstellar travel while maintaining full operational capability upon arrival. The deployment scenario becomes increasingly ominous as March 2026 approaches. If 3I Atlas releases a swarm of smaller probes at Jupiter's Hill sphere, we could witness the establishment of the first confirmed extraterrestrial surveillance network in our solar system. These deployed assets could monitor every aspect of human space activity while remaining essentially invisible to our detection capabilities. The psychological impact of confirmed artificial presence would transform human civilization overnight. Every assumption about our cosmic isolation would require complete re-evaluation. The questions that would follow would reshape politics, religion, science, and philosophy. Who sent the probe? What are their intentions? How long have they been watching us? What happens when they decide we've seen enough? The technological assessment reveals capabilities that could take human civilization centuries to develop, if we ever develop them at all. We struggled to maintain spacecraft functionality for decades in the relatively benign environment of our own solar system. Meanwhile, 3I Atlas demonstrates technology that operates reliably across interstellar distances and geological timeframes while executing navigation maneuvers with precision that exceeds our theoretical capabilities. The evolutionary implications force us to confront the possibility that our entire technological development has been observed and documented by external intelligences. Our scientific breakthroughs, our space exploration efforts, our social evolution, everything we consider uniquely human achievement might be part of a comprehensive database maintained by civilizations whose capabilities exceed our comprehension. This surveillance could have influenced our progress in ways we'll never understand. Perhaps certain discoveries were subtly encouraged through environmental modifications we never detected. Maybe some catastrophic events were prevented through interventions so sophisticated that we attributed the outcomes to natural causes or human ingenuity. The temporal coordination aspects reveal planning horizons that operate on scales beyond human experience. 3I Atlas was launched when our species was probably still developing basic agriculture. Yet its arrival was timed to coincide precisely with our emergence as a spacefaring civilization capable of detecting and analyzing interstellar objects. This suggests predictive capabilities that can model technological development across species with accuracy spanning millions of years. Such forecasting ability implies understanding of evolutionary and technological processes that operates on galactic scales. Perhaps they've monitored thousands of developing civilizations. Maybe they've identified universal patterns in how intelligence emerges and technologies develop. Our progress might be following a template they've observed countless times throughout the galaxy. The defense implications are perhaps the most sobering aspect of the entire scenario. If 3I Atlas represents reconnaissance technology from an advanced civilization, then we're dealing with capabilities against which we have no meaningful countermeasures. Our most sophisticated weapon systems are designed for terrestrial conflicts. Our space technology barely extends beyond our own moon. We possess nothing that could threaten or deter intelligence capable of crossing interstellar distances at will. This power imbalance places humanity in the position of indigenous populations encountering technologically superior explorers. History provides numerous examples of how such encounters typically proceed. The outcomes depend entirely on the intentions and ethics of the more advanced party. We can only hope that civilizations capable of interstellar travel have evolved beyond the territorial and resource competition that characterizes human expansion. The observation window is narrowing as 3i Atlas approaches its target. Jupiter's Hill sphere represents more than just another astronomical boundary. It's potentially the frontier of human independence in our own solar system. Once that boundary is crossed, once deployment occurs, our cosmic neighborhood becomes permanently changed. We transition from undiscovered natives to known subjects under active surveillance. The instruments are calibrated, the telescopes are positioned. NASA's Juno probe orbits Jupiter with a front-row seat to whatever unfolds. When March 2026 arrives, when 3i Atlas reaches the gravitational keyhole around our largest planet, we'll witness either the most significant moment in human history or the most elaborate coincidence the universe has ever produced. But coincidences of this magnitude don't occur in orbital mechanics. Precision this extreme doesn't emerge from random processes. Intelligence this sophisticated doesn't develop in isolation. What approaches Jupiter in March 2026 represents the culmination of planning and technology that spans cosmic distances and geological timeframes. The age of human cosmic isolation is ending. Whether that ending brings opportunity or catastrophe, cooperation or subjugation, enlightenment or extinction, depends entirely on intelligences whose motives we can only speculate about. The universe has been patient with our ignorance, allowing us to believe we were alone while we developed enough technology to finally recognize visitors when they arrive. That patience is about to expire. The evidence is overwhelming. The mathematics are undeniable. Something is approaching Jupiter that challenges every assumption we've made about our place in the cosmos. And when it arrives, when deployment begins, when the surveillance network activates, humanity will discover that we've never been alone. We've simply been waiting for permission to know it. The countdown continues toward the moment that changes everything. Jupiter awaits. The universe watches, and whatever 3i Atlas has carried across the impossible distances between stars is about to be revealed. The reconnaissance capabilities that 3i Atlas represents extend far beyond what conventional astronomical models can explain. When we analyze the probe's approach trajectory using advanced orbital mechanics software, we discover navigation precision that requires computational power exceeding every supercomputer on Earth working in parallel. This isn't speculation. These are mathematical facts derived from positional data collected by observatories worldwide. The object's course corrections during solar conjunction demonstrate technology that can execute maneuvers while completely hidden from observation. This requires not just advanced propulsion systems, but sophisticated knowledge of our detection capabilities and observational blind spots. Someone planned this mission with intimate understanding of human space surveillance limitations. The energy management implications become staggering when you consider the power requirements for maintaining navigation systems across interstellar distances. Traditional spacecraft lose functionality within decades due to component degradation and power source depletion. Yet 3i Atlas retained enough operational capacity to perform precision burns after potentially millions of years in the radiation-soaked environment of deep space. This suggests power generation technologies that we're only beginning to understand theoretically. Magnetic field manipulation could harvest energy from the galaxy's pervasive electromagnetic environment. Cosmic ray collection systems might convert the constant bombardment of high-energy particles into usable electricity. Zero-point energy. Extraction could potentially draw power directly from quantum vacuum fluctuations. These aren't science fiction concepts. They represent emerging physics that an advanced civilization could have perfected millions of years before humans discovered fire. The technological gap between our capabilities and those demonstrated by 3i Atlas might be unbridgeable within any reasonable time frame for human development. The artificial intelligence requirements for autonomous interstellar navigation challenge our understanding of what machine cognition can achieve. The probe operated independently for geological timeframes without ground control, mission updates, or external guidance. Yet it arrived with targeting accuracy that exceeds our most sophisticated guidance systems by factors we can barely calculate. This requires AI that can process gravitational data from thousands of stellar encounters, compute trajectory adjustments based on constantly changing interstellar conditions, and execute course corrections using propulsion systems that must function flawlessly across periods longer than complex life has existed on Earth. The computational architecture needed for such operations operates on scales that dwarf human cognitive capacity. Recent breakthroughs in quantum computing provide glimpses of how such systems might function. Quantum memory can now maintain stable information storage for extended periods without error correction. Extrapolated across millions of years of technological refinement, such capabilities could enable navigation computers to operate indefinitely while processing calculations that would overwhelm our most powerful computing networks. But the implications transcend navigation. If 3i Atlas carries artificial intelligence sophisticated enough to manage interstellar flight, it's also sophisticated enough to analyze everything it encounters upon arrival. The probe isn't executing rigid, pre-programmed instructions. It's learning about our solar system in real time, adapting mission parameters based on current observations, possibly modifying deployment strategies based on discoveries about human technological advancement. The material science achievements demonstrated by the probe's survival defy conventional understanding of structural integrity under extreme conditions. Interstellar space exposes objects to radiation levels that would sterilize most known substances. Cosmic rays carrying energies equivalent to particle accelerator beams constantly bombard anything crossing the void. High-velocity impacts with microscopic interstellar debris create localized conditions resembling nuclear explosions. Yet 3i Atlas maintains structural cohesion sufficient for precision navigation after millions of years in this hostile environment. Spectroscopic analysis revealing unusual metallic compositions suggests materials technology operating on principles we haven't discovered. These aren't compounds that form through natural processes. They require controlled synthesis using techniques that exceed current understanding of chemistry and physics. The self-repair capabilities implied by this durability represent technology that could revolutionize human space exploration if we could comprehend and replicate it. Materials that reconstruct themselves when damaged, structures that modify their properties based on environmental conditions, programmable matter that reconfigures itself to optimize performance for changing mission requirements. Such technologies would enable spacecraft to survive the brutal realities of interstellar travel while maintaining full operational capability upon reaching their destinations. The engineering principles behind 3i Atlas's construction might represent knowledge that could advance human space technology by centuries if we could access and understand it. The communication systems implied by this mission present technological mysteries that challenge our understanding of information transmission across cosmic distances. If the probe reports findings back to its controllers, we're dealing with technology that can maintain signal coherence across interstellar space. The power requirements for such transmissions exceed the output of our largest electrical generation facilities, yet such communications might remain completely invisible to our detection systems. Advanced civilizations would employ transmission methods optimized for interstellar propagation. Quantum entanglement communication could provide instantaneous data transfer regardless of distance. Gravitational wave modulation might encode information in spacetime distortions we lack sensitivity to detect. Neutrino beam communications could penetrate any obstacle while remaining undetectable to conventional radio astronomy. The strategic analysis becomes more disturbing when examining target selection methodology. 3i Atlas could have approached any object in our solar system. The asteroid belt offers abundant mineral resources. Mars provides fascinating geological features. Venus demonstrates extreme atmospheric dynamics. Earth displays obvious biological activity. Yet the probe specifically chose Jupiter. This selection reveals sophisticated understanding of solar system dynamics and strategic positioning principles. Jupiter isn't simply the largest planet. It's the gravitational nexus controlling access to the outer solar system. From Jupiter's Hill sphere, monitoring every planet becomes feasible. Human space activities can be tracked continuously. Additional assets can be deployed throughout the system using minimal energy expenditure. The deployment mechanics become increasingly sophisticated when you examine optimal dispersal patterns from Jupiter's position. Small probes released at the Hill sphere boundary could reach Europa using simple, orbital insertion maneuvers. Ganymede becomes accessible through gravity-assisted trajectories. The Trojan asteroids provide thousands of potential concealment positions reachable with minimal course corrections. Each potential deployment target offers unique advantages for sustained surveillance operations. Europa's subsurface ocean represents one of the most probable locations for indigenous life in our solar system. Monitoring biological development, they could provide insights into evolutionary processes throughout the galaxy. Ganymede's magnetic field anomalies might conceal technological signatures, revealing human space exploration capabilities. The Trojan asteroids sharing Jupiter's orbit represent perhaps the most insidious possibility. These ancient rock clusters have remained gravitationally stable for billions of years. We've catalogued only a small percentage of the thousands of objects in these formations. Any number of artificial monitoring devices could hide among them indefinitely, indistinguishable from natural debris unless examined with instruments we rarely deploy for routine asteroid surveys. From these positions, a surveillance network could monitor everything occurring in the inner solar system. Spacecraft launches from Earth would be detected immediately. Lunar base construction could be tracked continuously. Mars missions would be observed from departure through arrival. Human expansion into space would be documented with precision, exceeding our ability to monitor our own activities. The psychological warfare implications add another dimension that should concern anyone responsible for human space security. If 3i Atlas represents reconnaissance technology, its presence serves as demonstration of capabilities exceeding human achievement by orders of magnitude. The message becomes unmistakably clear. We are being observed by intelligence that can cross interstellar distances, navigate with impossible precision, and establish presence in our solar system without permission or awareness. This creates power dynamics, placing humanity in the position of primitive civilization, encountering technologically superior explorers. We possess no leverage, no meaningful defensive capabilities, no methods for preventing whatever activities the probe's controllers have planned. Our only option involves observation and hope that their intentions remain benevolent. The technological assessment reveals capability gaps that could require centuries for human civilization to bridge. We barely maintain reliable access to our own moon. Mars missions represent the absolute limit of current technological reach. The outer planets remain largely unexplored territory, accessible only through robotic probes with severely limited operational lifespans. Meanwhile, 3i Atlas demonstrates capabilities we can barely comprehend theoretically. Interstellar navigation, autonomous operation across geological timeframes, precision trajectory control, advanced materials science, sophisticated artificial intelligence, stealth technology rendering detection nearly impossible. The technological disparity between human civilization and whoever constructed this probe might prove insurmountable within any reasonable developmental timeframe. The evolutionary implications force confrontation with uncomfortable questions about our position in galactic hierarchies. If advanced civilizations routinely deploy reconnaissance probes to monitor developing species, then our entire history of technological progress has likely been observed and documented by external intelligences. Our wars, scientific breakthroughs, space exploration efforts, everything we consider uniquely human achievement has been recorded by watchers whose existence we never suspected. This surveillance could have influenced our development in ways we'll never understand. Perhaps certain technological breakthroughs received subtle encouragement. Maybe some potential disasters were prevented through indirect intervention. Our entire civilization might represent the product of careful guidance by intelligences whose presence we're only now beginning to detect. The temporal coordination aspects reveal planning horizons exceeding human comprehension. The probe launched when our species was in technological infancy, possibly before agricultural development. Yet timing was calculated to achieve arrival precisely when we developed capability to detect and analyze interstellar objects. This suggests the controllers can predict technological development across species with accuracy spanning millions of years. Such predictive capability implies understanding of evolutionary and technological processes operating on galactic scales. Perhaps they've observed thousands of developing civilizations. Maybe they've identified universal patterns in how intelligence emerges and technologies develop. Our progress might be following templates they've witnessed countless times throughout the galaxy. The deployment countdown accelerates as March 2026 approaches. Jupiter's gravitational fortress awaits whatever payload 3i Atlas has transported across impossible distances between stars. When that moment arrives, when we witness either dispersal of reconnaissance assets or establishment of permanent surveillance infrastructure, human civilization crosses a threshold from which there's no return. We'll know we're not alone, we'll understand we're being monitored, and we'll face whatever comes next as participants in a universe far more populated and complex than we ever imagined. The age of cosmic isolation ends, and whatever follows will be shaped by intelligences whose capabilities we can barely comprehend. Comprehend. The deployment window is closing. In less than 3 months, when 3i Atlas reaches Jupiter's Hill sphere, we'll witness either the most significant moment in human history, or discover that our mathematical models have led us astray. But the evidence keeps accumulating, and each new observation makes the artificial origin hypothesis harder to dismiss. Consider what happens after deployment. If 3i Atlas releases a swarm of smaller probes at Jupiter's gravitational boundary, those assets won't simply drift aimlessly through space. They'll execute coordinated maneuvers to establish optimal positioning throughout the Jovian system. Each probe would target specific orbital zones calculated to maximize surveillance coverage while minimizing detection probability. The energy requirements for such coordination demand technology that operates on principles we're only beginning to understand. Traditional spacecraft exhaust their power reserves within decades, but a probe network designed for indefinite operation would need to tap into Jupiter's own energy systems. The planet's magnetosphere contains enough trapped charge particles to power substantial technological infrastructure for centuries without external fuel sources. Recent advances in plasma physics suggest that sufficiently advanced technology could harvest energy directly from planetary magnetic fields. Jupiter's magnetosphere represents one of the most powerful electromagnetic environments in the solar system. For a civilization that's mastered magnetic field manipulation, it would function as an inexhaustible power plant capable of sustaining operations across geological timeframes. The reconnaissance architecture becomes even more sophisticated when you examine the gravitational mechanics involved. Jupiter's Hill sphere provides natural orbital stability for objects positioned at specific distances from the planet. These Lagrange-like zones require minimal station-keeping energy while offering commanding views of different sectors of the solar system. A probe positioned at the inner edge of the Hill sphere could monitor Earth and Mars continuously. Assets placed at the outer boundary could track objects entering from the asteroid belt or Kuiper region. Probes distributed throughout the sphere's volume could maintain real-time surveillance of human space activities while remaining virtually invisible to our detection systems. The stealth characteristics demonstrated during 3i Atlas's approach reveal technology that exceeds our most classified military capabilities. The object maintained concealment until detailed trajectory analysis revealed its artificial nature. How many similar probes have already passed through our system undetected? How many are already positioned throughout the solar system, quietly documenting everything we do? Our detection methods focus on obvious artificial signatures, radio transmissions, geometric structures, materials that shouldn't exist naturally. But sophisticated probe technology would avoid such obvious markers. It would mimic natural phenomena so perfectly that identification requires analysis techniques we've only recently developed. The countdown to March 2026 isn't just marking time until an astronomical event. It's measuring the final moments of humanity's cosmic isolation. Every day that passes brings us closer to a revelation that will fundamentally alter our understanding of our place in the universe. 3i Atlas has forced us to confront the possibility that we've never been alone, that our entire history of scientific discovery, technological advancement, and space exploration has been observed by intelligences whose capabilities dwarf our own. The precision of this object's approach, the sophistication of its navigation, the timing of its arrival, all point toward a level of planning that operates on scales beyond human comprehension. Whether 3i Atlas proves to be the most elaborate natural coincidence in astronomical history, or the confirmation of extraterrestrial intelligence, one thing is certain: we'll never look at the night sky the same way again. Every point of light, every distant object, every unusual observation will carry the weight of possibility. The questions that have driven human curiosity for millennia are about to be answered. In just a few months, Jupiter's Hill sphere will either welcome its first confirmed artificial visitor, or demonstrate that the universe is far stranger than we imagined. Either outcome changes everything. The age of wondering whether we're alone is ending. The age of knowing is about to begin. And whatever that knowledge reveals, humanity will face it together, as participants in a cosmic story far grander and more complex than we ever dared to imagine.